As usual, I have put together a demo notebook for you here. You can find the Lynette in TensorFlow notebook already created for you in the notebooks directory. And we are going to build upon the intermediate net that we had in this demo to create that Lynette in TensorFlow notebook. So I'm just going to copy the intermediate net that we just finished. So we're going to make a copy, and I can close the original. Then I'm going to rename this to something more sensible, like Lynette in TensorFlow. And this Lynette in TensorFlow, just like the last notebook, it follows the style of an Americ Damian notebook, which has a really clean way of looking through the training in particular. But we've developed on that to clean up the variables at the top, and we are using this to build very specifically the Lynette that we built in Keras here earlier. So you're going to be able to compare this Lynette in Keras notebook side by side with the Lynette in TensorFlow notebook that we are creating over the course of this demo here. So let's change the name here. This is going to be Lynette 5 in TensorFlow, and we're loading the same dependencies. Let's clear out the cells, restart and clear the cells. So we're starting afresh here with a nice clean slate. So our dependencies are the same as in the last notebook. We're going to load the data in the same way. We are going to have slightly different neural network hyperparameters. So we're not going to have a learning rate specified anymore. We're going to be using Atom instead of the vanilla gradient descent that we used in the last notebook. And so we'll just use the default parameters that Atom comes with later on. We can train for 10 epochs again. That seems fine. We can leave our batch size at 128. That should work fine. And we can leave our weight initialization the same as well. I'm just going to make this name a little shorter because it was a little bit cumbersome to work with earlier. So we're going to call it weight initialization short form like that. And then also, this network's going to be a bit deeper. It's going to take longer to run each epoch. So we're not going to want to wait till the end of each epoch to see how the network's coming along. We're going to want to output little notifications along the way that the network is still running and training well. So we're going to display our progress after every 40 mini batches. So let's set all that. Oh, we haven't loaded anything. We have to load everything, of course. Now this network, if you look back at the Lynette 5 net in Keras notebook, we have quite a few more layers. So we're going to need to specify parameters for all of these layers. So let's create a little subtitle here. This is a code notebook, but above it, we're going to create a little note which says set parameters for each layer to help us out later on. And now we have so many layers, we're actually going to have some comments in here to make it easier to identify. So our input layer stays the same. We still have 784 inputs. Our first convolutional layer, as we have here, is going to have 32 neurons or kernels or filters, however you want to call it. The kernel size is going to be 3 by 3 pixels. So let's define all of that. Let's move this down. So our first convolutional layer is going to have 32 neurons, and the size of the kernel is going to be 3 by 3. We can just write 3 because we know it's going to be a square. And we're going to define the second convolutional layer in a similar way. So looking back at our Keras notebook, it's going to have 64 neurons, and it's going to have the same size patch. And then we're going to have a max pooling layer. So our max pooling layer we said is going to have a pool size of 2 by 2. So we need to specify that here as well, pool size of 2. And we decided we were going to have dropout in that layer, so we should specify that here too. So our max pooling layer dropout is equal to 0.25. What's next? We have to flatten things. We don't need to specify any parameters there though. And then we have a dense or fully connected layer. So let's add that in here, some parameters. So how many dense neurons are we going to have? Well, we're going to have 128 of them. And ReLU activation, that's fine. We're also going to have a dropout of half of the neurons on each step. So let's specify a parameter for that too for later on. All right. Now the only thing left to do is specify how many classes we have in the output layer, and that stays the same. So that's easy. That's still just 10 possible digits. Great. Now we need to define our placeholder tensors. That's the same as before, so we can just run that cell. We need to define our types of layers. So our dense layer is already here. Let's write a little note for ourselves. So this is a dense layer with ReLU activation. And then we're going to create a couple more layers with the same kind of syntax. So we're going to create a convolutional layer, also with ReLU. So we'll define it to have similar kinds of parameters. So it also takes in x and w and b, the x and the weights and the biases. But we also need to specify a stride length. And we used the default in Keras earlier, and that was 1. So we'll just do that again here now. So we're going to do this step by step. We're going to create our z. We're actually going to break it into 2 steps where we create the result of matrix multiplication of x and w first. So we're going to call that new matrix xw. And to do that, we're going to use the conv2d layer that TensorFlow provides for us. We're going to feed into it x and w. And we're going to set the strides to this shape. You're with a 2-dimensional image. You're going to, I think, always start with a 1 here is the first element of this array, and a 1 at the end as well. And then we want to have the same padding through here. So that creates our xw. So we want to create our z. To do that, that's pretty simple. We do it the same way as we did in our dense layer and as we have been doing in our TensorFlow notebooks. So we use add, but because of the shape of these matrices, we want to be careful that we're adding them properly. So we're going to use the bias add function, which is specifically designed for this circumstance. And then finally, now that we have our z, we want to perform our ReLU transformation to output our activation A. And so we just simply call on the ReLU function, and we return A from this little convolutional wrapper. Now we have one more kind of layer that we're going to define, our max pooling layer up here. So we've already defined our dense layer, we've defined our convolutional layers. Now let's define our hidden max pooling layer here. So max pooling. Now that doesn't have any activation, so we don't need to specify that. So max pooling 2D. It's going to take in its input, and then all we need to do is tell it what our pool size is going to be. And we can do this all in one line. So this is just a little simple wrapper here to clean up our code later on. If we were going to add more max pooling layers, it would save us typing and just makes everything look kind of nice. So the kernel size for for our max pooling layer is going to fit the same kind of notation as here, starting with a 1 in the array, ending with a 1 in the array, and indicating the pool size in the middle, because we're not dealing with an excessive amount of dimensionality here. These are still just two-dimensional images, so we don't need to worry about the third or fourth dimension. And so the kernel size is going to be equal to the pool size, of course, too. And our stride length, which we didn't have to indicate specifically in Keras, it was just assumed to be equal to the pool size. We're going to make that explicit here. So we're saying that the number of strides is equal to the pool size, so we don't have any overlap as our max pooling layer strides over the image. And the same kind of parameters above. We're setting the padding equal to the same. We're not going to change the buffer around the edges of the image. We're going to leave the padding the same. All right, so there we go. We've defined our layers. And now we need to define our neural network architecture. Of course, it's not going to be the same as the last time around. So I'm actually going to simply delete some of this. The output is going to be similar, so we can leave that for now. These dense layers are going to be different. We're going to be passing a few more variables into this function as parameters. So the number of inputs we're going to need the pool size. For the max pooling layer, we're going to need to pass in our dropout parameters. That should be all we need. At the beginning of these live lessons, we were taking the imness digits as 28 by 28 images, and we were converting them into 784 by 1 array. Now we're doing the opposite. So in TensorFlow, the default is to give it to us 784 by 1. So here we need to take those and shift them into the 28 by 28. So to do that, we need to reshape input data. So what are the dimensions of our square image? Well, it's simply the square root of the number of, so we know that we have 784 pixels. So to make that into a square image, we know that the length of the square is going to be the square root of 784, which is 28. And then we can actually reshape our 784 length array to a square shape. So we feed in our x, and then we define the shape that we want to reshape it to. So it's just going to be a square in 2 dimensions. Don't need to worry about the third or fourth dimension with these images. And now we can start defining our network shape. So we start off with 2 convolutional layers. So let's define those. So our first convolutional layer is equal to conv2d, which is the function we created up here. We're going to pass in our square-shaped inputs. We're going to define our weights next. The shape of our weights and our biases. So that'll happen in the dictionary step down here. So we need to make some changes here to accommodate our convolutional nets, but it's the same kind of idea, defining our variable dictionaries. And so convolutional layer 2 is going to look a lot like convolutional layer 1, so we just copy and paste. Now our input is going to be the output from convolutional layer 1 here, gets input into the second layer. We're going to have slightly different shape of our weights and biases. And then that convolutional layer feeds into this max pooling layer. So let's define that. So pool 1 equal to max pooling 2d, function we defined up here. Take the output from the previous layer as an input here. And this doesn't have its own weights or biases that need to be trained. So all we need to pass into there is the MP size, pool size, and we're going to have dropout. So let's add the TensorFlow dropout function to the output from here. And the TensorFlow dropout function is selecting the probability that we retain neurons, which is the inverse of the way Keras does it. So we need to invert our MP dropout here. So subtract the MP dropout that we defined to 0.25 from 1 to get that 0.25 dropout that we wanted in the same kind of format as Keras. So that defines all of our convolutional layers. We're nearly done defining this network. So we've gotten through all of these layers now. So we need to flatten our outputs from multiple dimensions into one for our dense layer. So to do that, we have our dense layer. We're going to flatten it with the reshape function. And we're going to input these values into that reshape function. The shape that we want is flat. We have slightly different weights that we need to pass in here. We'll get to that in the dictionary in a second. And so then once we've flattened our data into 784 by 1 array, which is all that this definition here is saying. So we're using information that we're going to define later on here. That will be the, not 784 rather, this will be the number of neurons in our dense layer. So we defined that up here to be 128. That's it. So now the dense layer we defined above right here. So it takes in the weights, or the x first. So that's this, flat from the previous calculation. It has its particular shape, 128 by output layer neuron, and it has the same number of bias neurons. And then finally, we're going to have some dropout as well. So we can define that in the same way as we did here. So taking this layer's output as the dropout input and setting it to 1 minus the dense dropout for the same reason that we did above here. All right, and then we have our output layer, which is the same, except that it's now taking the output from here, this layer, dense 1. It's the only change we have to make there. It's outputting output layer Z, all right. And now we just need to make a couple of changes to our bias dictionary. So we change names around a bit here. So biases have this new annotation, B convolutional 1, bias convolutional 2. And we have to get the lengths right here. So let's make sure that we change these names as well. Convolutional 1, convolutional 2. And we also have a dense layer, which we labeled bias D1, and it is of length n dense, which we defined all the way up there, yep. And our B out is the same as before, so we can leave that as is. Now we have a little trick here to calculate. I'm going to get to that in a sec. Let's first start with all the information that we do have. So we change this naming scheme around to weight C1. We have the first parameter here is just that name. And the shape here is quite a bit different than we had been seeing because this is a convolutional layer with more than 2 dimensions, so we need to define it as such. So we actually have 4 dimensions that we need to worry about here in the convolutional layer. So we have the length and the width of the patch on the kernel, so those are the same. We have a 3 by 3 patch moving around on the convolutional layer. And then we have this placeholder 1, just 1 dimension for this first convolutional layer that can stay as 1. And we have the number of convolutional neurons that we define for that layer up here. So that's 32. And our initializer is the weight initializer. So that's all good. Now the second convolutional layer's weights are going to look almost the same. So let's copy and paste. So here, rename it WC2, and it's the shape, still 3 by 3. However, now we have the shape needs to match so that we can be doing matrix multiplications here. So we take the shape of the output from the first convolutional layer as the shape of the input into the second convolutional layer. So that starts to explain why we just needed to have a 1 here. We didn't need to worry about anything passing in with a particular shape yet. And then our output is going to be however many neurons we have in convolutional layer 2, which we specified to be 64. Ooh, I need to change these up here. Missed that. Then we have to define our dense layer, which is similar to this convolutional layer above. So here, the dense layers, as we've seen, don't have to worry about the convolutional kernel dimensions. So it's simply taking, for its matrix multiplication, it's taking the output size from the previous layer. However, we pass that through a max pooling layer on the way. So we change the size. So we need to do some quick calculations here. So the full square length, the square dimensions are 28 by 28. So that's the square root of 728, our number of inputs. And then the pooled square length is a subset of that. So the size of the pooled square has a length that is half, because our pool size is 2. So the length of our square is halved in 2. And then the number of dense inputs that we have is the pooled squared length squared times the number of neurons that we have in our second convolutional layer. So now we know how many inputs we have into this dense input layer. The output is however many neurons we have in it, which is n dense. And then that's the shape of the inputs into W out and dense. And of course, the output is the number of classes. So that's the same. And we need to change this to weight init. Let me shorten that variable name. There we go. That's all set. I didn't run that after I made that fix up there. So there we go. That'll run fine now. And finally, we're ready to get our predictions out. So this is the same as before, but we have a few more parameters in our network than we did before. So we just need to be careful that we pass those in. So these first 3 are the same as they were in our last notebook, but now we're passing in a few additional things. So the number of inputs, the pool size, the MP layer dropout, and the dense layer dropout. These are simply the parameters that we defined up here, passing them in. All right, so we have this error that came out. And with all this code that I wrote, I had one little fat finger, which is that the input into this ReLU activation should have been Z in the previous line, not A itself, of course. So there was a self-reference there. Now, having fixed that quickly, we can restart, and we can run all the way down to here. And everything will be hunky-dory. There we go. All right, so now our cost is the same as before. We're still just using categorical cross-entropy. We're still optimizing, not with vanilla gradient descent, however, but with atom optimizer. And so we don't need to pass learning rate into there. We're simply going to say that we're minimizing cost. And our evaluation metrics are staying the same. Our initialization operation is staying the same. And our run of the network is staying largely the same as well, except that we're going to offer ourselves some reassurance that something is happening over these long trainings of epochs. So if our range divided by our display progress parameter that we set way up here to 40 batches, if that division has no remainder, so if the modulo is equal to 0, then print some additional information. So we just want to print that we've stepped. And so to do that, I'm going to grab the line instead of typing it all out manually I did earlier. So let's just paste it in there. And so this is just going to give us some progress reports as we train. So we have this output that we're going to be training for 10 epochs, and we now have this little bit of reassurance here that something's happening. So every 40 epochs, we get an output that we've reached another step. And by the end of a single epoch, we will see that we have 92% accuracy, which is awesome. And by the end of 10, we'll have over 99% accuracy. So there's certainly no time to sit here watching it happen in this code demo, but you can try that at home. And it's awesome. This is, in many ways, this is the fruits of all of our labor here. So we started off these live lessons by talking about these really incredible convolutional neural networks that are able to recognize objects with incredible precision and with an ability to recognize features themselves as opposed to having to code up features manually. And then we went over all of the theory of how neurons work and how we create networks of neurons, the various options that we can set to be doing those calculations. We leveraged many of those options in building this Linnet 5 notebook in TensorFlow. And we had to take all of our knowledge of TensorFlow that we built up over several graph demos as well. So congratulations, you've made it here, and we've built this beautiful neural network. Nice work.